These aircraft are landing on rebuilt tires. Let's take a close look at what happens to a tire in an arrestment. These rebuilt tires will log more landings than a new tire and will save the taxpayer approximately 75% of the cost of a new tire. Knowledgeable naval aviators know that a rebuilt tire is as good as or better than a new tire. This film on rebuilding naval aircraft tires will show you why a rebuilt tire is as good as or better than a new tire. The airlines have been using rebuilt tires for more than 10 years with great success and sizable cost savings. The rebuilt tire's success story begins with the original tire, which must prove itself by successfully completing its first service tour. Before showing you how the tire is rebuilt, it is necessary to show you quickly how the tire is made originally. A tire is basically rubber tread, which provides traction and resists wear and abrasion, and nylon thread, which is woven to make up the cord body and coated with rubber. This gives the tire strength and flexibility. The tread is made of a special and usually secret compound of rubber, sulfur, and carbon black. This compound is fed into an extruding machine, which forms it into the required shape for the tire building process. The beads are made of high tensile steel wire, bonded with rubber and covered with fabric. These beads anchor the tire to the wheel rim. The tire builder wraps the rubberized fabric around a drum to build the tire foundation, or carcass. He then places the beads into position and wraps the sides of the fabric plies, or layers, around the beads. Next, he wraps the rubber tread and sidewalls around the drum over the rubberized fabric. The drum is collapsed, and the uncured tire, in the shape of a barrel, is ready for molding and vulcanization. This is done in a bladder or bag-o-matic press. The press opens automatically, and the manufacture of the new tire is completed. The new tire is made to rigid specifications, tested on the dynamometer, and approved. But these are the last controls placed on the manufacturer of a new tire before it is placed into service. During its first service tour, the new tire is stretched by inflation, deflected by landings, and in time becomes stabilized through use. If the new tire lasts through one tread wear out, the carcass or foundation of the tire has proven itself and is eligible for rebuilding. We will first see how a tire is rebuilt, and then examine how a Navy tire rebuilder becomes qualified and remains qualified. One of the 5 qualified tire rebuilding contractors receives eligible Navy tire carcasses for rebuilding. The carcass is first put through an extremely thorough inspection cycle. If it does not meet inspection criteria, it is immediately rejected for rebuilding. Information embedded in the tire is highlighted with crayon. A color-coded process card is written up on each carcass. The card stays with the carcass through the entire rebuilding process. The inspection cycle is preceded by removal of the balance pads, since the rebuilt tire will have its own static balance requirements. A heat lamp is used to soften the gum on the back of the balance pad so that it can be pulled out without damaging the inner liner, which keeps the air in the tire. The inner liner replaces the inner tube in a tubeless tire. The inspector checks the inner liner by injecting 100 pounds of air into the tire. After the required injection time, he sprays a soap solution all over the inside and outside of the tire. He then looks for excessive inner liner leaks which cannot be repaired, or bulges caused by large ply separations in the tire. Another cause for rejection: breaks into the cord body. Instead of a simple leak or crack in the liner, the breaks will actually be broken plies under the liner. When he sees that the vents are bleeding, he knows that the casing is loaded with air. The vents are necessary to relieve pressure buildup in the carcass. The tire may have been subject to excessive brake heat, causing the rubber in the bead area to lose resiliency and become brittle. Bead face leaks, or any type of separation anywhere, is immediate cause for rejection. So much for the inside of the tire. Causes for rejection on the outside include breaks in the cord body or severe sidewall cracks called weather checking, caused by oxidation of the rubber. Other more obvious causes for rejection are skid burns, where the wheel locks and the tread is worn down too far into the plies. Foreign object damage, excessive wear, or too many previous rebuildings. It is the responsibility of the rebuilder to determine the suitability of all carcasses, not only here, but throughout the rebuilding process. After the carcass has passed inspection, it is placed in a 170-degree Fahrenheit room overnight to round out the flat spot which occurs on nylon fabric tires. With the flat spot removed, the tire will turn true. This is necessary to properly buff the tread-reinforcing nylon belt found in all high-speed, high-performance tires. The automatically controlled buffing machine removes the old oxidized tread from the tire and puts a proper shape and profile to the tire in preparation for rebuilding. Three checkpoints are made on the carcass to see if the thickness of the under tread remaining is sufficient for rebuilding. After buffing, the carcass is again inspected and cleaned. If there is a cut, it must be skived out with a tungsten carbide rasp. There is a limit on the penetration of the cut. The quality control inspector rechecks every carcass and initials the process card. Many carcasses are rejected here in spite of all the work that has been done to this point. If there are remnants of cored edges after skiving, they must be defuzzed before the application of rubber cement. After brushing, rubber cement is applied by a special pumping system designed to keep the cement pure. Another inspection is made prior to passing the tire on to the next step in the rebuilding process. Next, a reinforcing band is rolled onto the carcass to make the tire turn more true at high speeds. This band corresponds somewhat to the belt in belted tires for passenger cars. The reinforcing band is made up of layers of nylon and rubber which have a shelf life that cannot be exceeded. After the band is put on, it is washed with rubber solvent to take off handprints or any other marks. Now the orbit tread, an electronically controlled tread builder, goes to work. Rubber material goes into the extruder screw. The friction of being extruded raises the temperature of the rubber to about 205 degrees, and what comes out is a hot ribbon of rubber. Tread rubber, about 1/10 of an inch thick, is applied in overlapping layers, which will result in a tread thickness of 13/32 of an inch after vulcanization. Before the tire is put into a mold for curing, it is dynamically balanced to virtually eliminate the necessity of balance pads. This machine spins the tire, senses the degree and angle of unbalance, stops the spinning, and brings the light spot of the tire toward the operator. He keeps adding strips of the same rubber tread material which is already on the tire until the unbalance has been reduced to no more than 3/10 of an ounce, the Navy limit. The 3/10 of an ounce is half of what is allowed by the airlines. Before the tire is placed into one of these curing molds, a heavy curing tube and curing rim are placed inside the tire. These support the air pressure inside the tire while it's in the mold. A unique mechanical method is used to reduce the diameter of the tire so that the mold and tire will fit tighter. What happens to the tire during the cure? The heavy-duty tube placed in the tire is inflated to 200 psi, forcing the raw rubber against the heated mold. This helps to shape the tread pattern of the tire. Curing takes up to 3 hours, and during that time, the electrically heated molds are kept at 315 degrees Fahrenheit through the use of thermistors. Thermocouples in the mold are used to record the temperature. The air pressure is also monitored, and the length of the cure is set by an electric timer. If at any time the pressure or temperature is off, a buzzer alarm is sounded. Pertinent data is entered on the process card. This curing process, known as vulcanization, changes the molecular structure of all the rubber, and thus the tire is rebuilt as one piece of rubber and fabric. After curing, any overflow on the tread or sidewall is trimmed. A new coat of rubber-based black tire paint is applied. The static balance of the rebuilt tire is then checked. As the tire turns on the rails, it finds any heavy spot which may exist after curing and trimming. A mark is made where the balance pad will be applied. The pad is temporarily taped to the outside of the tire to ensure correct balance before cementing it to the inside of the tire. Final balance is confirmed dynamically because the Navy insists on very high standards. Final visual inspection and special tire marking is done by one man who does only Navy tires. Information on the colored band is used by the Navy Supply Department for identification purposes. Final plant inspection, required only by the Navy, is an actual look inside the carcass of the tire to find separations between plies and the tire body. One method accepted by the Navy is holography. Let's remove the cover in order to visualize this inspection process. A ruby laser beam is split. One part of the beam goes to the film camera, and the other part hits the tire and then goes into the film camera, thus creating a double exposure. One exposure is made at atmospheric pressure, and a second exposure is made in a vacuum. Superimposing the two exposures makes the hologram. This process is repeated at 90-degree intervals around the tire. This is what a hologram of a ply separation looks like. A knothole effect. Obviously, a reject. Approved plant equipment for seeing inside the tire carcass is only a small part of what is required of the contractor before he can even bid on Navy work. For initial qualification, the contractor submits 2 rebuilt tires to the Flight Dynamics Laboratory at Wright-Patterson Air Force Base in Dayton, Ohio. First, these undergo air retention tests, where they stand for 12 hours. The loss of air cannot exceed 5%. Next, the tires are tested on the dynamometer. These tests include 10 to 15 simulated landings to check tread retention. The Navy requires a 60% load footprint, which is normally the aircraft weight minus the fuel consumed. A 100% footprint, or 100% rated load at rated pressure, and a bottom footprint showing the tire condition as it bottoms to the wheel flanges, as in catapulting. The tested tire is not put into service. It is only a sample tire which must be tested further at the Naval Air Development Center before the contractor can be qualified to rebuild Navy tires. NADC has the technical cognizance of all naval aircraft tire rebuilding. The NADC tire section does an original infrared trace on the tread to make certain that the rubber compound used in subsequent rebuilt tires matches the compound used on the qualifying tire. Strip adhesion between plies is tested. Tensile strength. Hardness. And specific gravity. All must comply with specifications. 10 additional tires are sent to be test flown at the Naval Air Test Center at Patuxent River, Maryland. The qualified rebuilder knows that, unlike the new tire, the Navy requires continuous monitoring of the quality of his rebuilt tires. The rebuilder uses this Monsanto rheometer to check samples of raw tread rubber received from his suppliers. The rheometer checks the raw rubber's scorch factor, plasticity, cure rate, and modulus. The Instron tensile tester is used to check the adhesion between plies. It also checks adhesion between the balance pad and the inner liner. Monthly, the Decasser representative randomly selects tires from the rebuilder's stock. These are shipped to one of the Naval Air Rework facilities, which performs tests like the original NADC qualifying tests. The NARF compares this data to the original qualifying data. NADC further monitors the contractor's performance by continually selecting rebuilt tires from Navy supply points and subjecting them to the original qualification tests. air retention, dynamometer, the infrared trace, tensile, hardness, specific gravity, plus a new one developed by the Naval Air Development Center, an ultrasonic pulse echo tire inspection system. It's like sonar. A pulse of ultrasonic energy is transmitted into the tire carcass by a transducer located in water 1 inch below the surface of the tire. A presentation shows normal sonar echoes as well as a flaw echo. These flaw echoes can be indications of possible ply separations in the tire. This is what ply separation looks like and can only be confirmed by destructive testing. Unlike new tires, where monitoring stops after the manufacturer has met initial qualification requirements, rebuilt tires must undergo random and continued non-destructive testing by holography, ultrasonics, and on the dynamometer. When necessary, the rebuilt tire is destructively tested. Flight testing also continues. All this to ensure flawless rebuilt aircraft tires, which will give the Navy more and better service at less cost to the taxpayer.